Here we go. We are 19.1, last chapter of the year, 19.1 on vectors. Today we're going to talk a little bit of the anatomy of a vector and notation of vectors. For you physics folks out there, this will be pretty elementary in nature. You can just kind of cruise along and observe and enjoy the show. Okay, so scalars. Scalars are quantities of magnitude with no direction. So like temperature, it's a number, right? It's a number. It has no direction. Volume, length, mass, time, even charge. Charge seems to have direction, but we don't consider it a vector. What we consider a vector is something that has both magnitude and direction. Pause for the folks on the web. You can just go YouTube it. So a vector doesn't necessarily have to do with crime, but it has both direction and magnitude. So magnitude will be like the distance or the length. Magnitude will always be positive. Okay, so let's get into some of our notes here. Typical notation that you'll see with vectors is this right here. One of these two. This is how you name a vector. Naming a vector. A vector typically has two letters, but it can have only one letter. The first letter will be where it starts, and the second letter will be where it begins. Begins? Ends. So, what's that? Is it going? It's going. It's going. Okay. I'm a professional, people. Okay, so we could call this vector xy, right? And I use this other notation. It only has half of the arrow. Some of you are going to be bothered by that, so if you're very particular about it, you can put another portion to the arrow. It's okay. All right, but that tells us the direction of the vector from x to y. All right, so I could actually rewrite vector xy as, check this out, vector negative xy or negative yx. That's the opposite direction, right? It negates the direction, just flips it the other way. Okay. Another way you might see a vector named is with one letter, typically a lowercase letter. This could be vector b. Typically with one letter, they don't put the arrow over the top, but I like to just because I like that symbol. It's kind of like mathematical gains in vector form. All right, and this right here, these absolute value bars, they're not absolute value bars. This is the symbol for the magnitude. Magnitude of the vector. So if the distance from A to B up here was 10, the magnitude of AB would be 10. Cool. That's what magnitude is. Right? Because direction is like the angle at which the vector is projected. Magnitude is the length of that vector, the distance traveled. So your magnitude will always be positive. Okay, equal vectors. Equal vectors are vectors with the same direction and same magnitude. Okay, so equal vectors have to be going in the same direction. Negative vectors are vectors that either head in the opposite direction as each other and have the same magnitude, or could just be this right here, where we say that xy is going to be the same thing as negative yx. Right? Those are negative vectors which are equivalent to each other. All right, those would have the same magnitude and direction. Okay, now the zero vector. Zero vector is interesting. If I took xy and I added yx to it, if I thought of that graphically, where would I end up? Well, here's xy, and then I added to it yx. Where would I end up? Right where I started. That's called the zero vector. Right, that's called the zero vector. Is it possible to add up more than two vectors and get the zero vector? an even number, I can do it with an odd number. Check this out. I'm going to go from x to y, and then I'm going to go from y to z. So there's vector xy, there's vector yz, and then all I need is zx to complete it. So if I add those three up, I get the 0 vector. Because look at that, it comes full circle from x back to x. Right, so that would be the 0 vector. Question in the crowd? All right, let's keep moving here. Okay, so let's just state one pair of each of these. All right, so stating this for part A, I want two vectors that have the same magnitude. Thoughts? Same length. The vectors are the same length. Doesn't have to have the same direction. Just fire off some letters here. A and B. Yeah, I'd say A and B, probably. Would you agree that D and F would have the same magnitude? Those look pretty good. I think I got that pretty well solidified in my head. Same direction. Well, let's name A and C. What else? D and F. B and E. Yeah, I'll go with B and E. Just keep it, wow, keep the variety in life. That's cool. Mix it up a little bit. Okay, part C. Opposite direction. G and A. G and A or C and G. Yeah. Either of those two pairings. Looks like those are the only two that go the opposite direction. Part D, vectors that are equal. I only have one pair. It'd be D and F, right? Same magnitude, same direction. And then parallel. Well, parallel is different than equal. Could they have different directions and be parallel? Yeah, sure. So I'd have A and C and G. Right? And then, of course, you got your DF pairing as well. For children on the web, these are not exclusive lists. There's probably other pairings that I haven't mentioned, but we're just trying to get the basics here. Okay. So, addition of vectors. Okay, so when adding vectors, I take my first vector and put the head of the first vector, right? Here's the head of the first vector right here. Here's the tail of the first vector to the tail of the second vector and finish with the head of the second vector. So the vector A plus B would be the vector that connects the tail of the first to the head of the second. That's A plus B. Okay. You drew a triangle using vectors. All right, now, what would A minus B look like, you think? What happened to B? A minus B. Are we going in the direction of B? No, we're going the opposite direction of B, but for the same distance. So A minus B, I like to think of A minus B as A plus negative B. So I sketch a nice little opposite of B right here. I'm going to drag that over. And when I go from tip of the first to tail of the second, let me get this out of the way. Move thing. All right, this will be, let's go with something ugly. Yeah. Brick red here. That would be A minus B. All right, now would A minus B and A plus B have the same magnitude? Maybe. Maybe, but not always. The case where they would have the same magnitude is if this were a 90. But it doesn't look to me like that's a 90, or at least not close enough for me to make that distinction. So we don't know for sure here. But if it was a 90, then yes. All right, let's look at, maybe draw a couple of these. For each of the following, draw A plus B. Okay, A plus B. So here's A. Here's B. Looks to me like there's A plus B in blue. That's our resultant vector. One of these I want to do A minus B. A plus B is just It's nice, but it's too simple for me right now. I'm going to do a plus b and a minus b for part F. There's a, here's b. So I think we can agree here's a plus b. That's a plus b. Oh, how about a minus b? There's negative b. We throw that on there. Ah, look at that. That's a case where a plus b and a minus b won't have the same magnitude. Okay, so let's do a creepy robot problem, and Marky Mark in a nice collared shirt there, pulling ropes on the safe. Apparently they're fighting over this. One of them's pulling this safe straight north, the other one's pulling it straight east. One of them is pulling at a larger force with a magnitude easterly, whereas the other one's pulling, I don't know, what is it, 40 north, the other one's 60 east, so it's going to move kind of in that northeast direction. You with me? Okay, so let's say Marky Mark here is pulling this direction at 60 newtons. And creepy robot, is pulling straight north at 40 newtons. There's a problem if I try to do this. What's the problem with that? Yeah, it's not tail to head, right? I got to orient it so it's tail to head. So it doesn't matter which way you go with this, but what I would do is probably drag this over here. So now I got tail to head, and look at that. That's actually really nice. Very nice to you. We gave you a right triangle. Why do you need to do that? Because in this scenario, I've got tail to tail right here at this axis. So I want tail to head. And so then when I connect that, I get a nice right triangle. And I'm going to find this 60 and this 40 are the magnitudes of those vectors. So I'm going to find the magnitude of the purple vector using Pythagorean theorem. But I'm going to drop the 0 there. I'm going to go 4 squared plus 6 squared equals the magnitude of our resultant vector squared. So I get 16 and I get 36. That's r squared. Oh, that was a good 2. I add them together, I get 52. I know a perfect square that goes into it's 4. How many times does 4 go into that? Divided into 2 is 26. Half of that would be 13, right? So I get 4 times 13. Well, what's the square root of 4? 2. So that is the magnitude of the, whoops, I don't want the square there anymore. Go away. Go away. There it is. But that's not the magnitude of the vector because I dropped the 0. So I'm going to add a 0 on there. And that's the magnitude of our vector. All right, so the amount of force that's placed on this is 20 root 13 newtons in that direction. If I wanted to, could I find this angle? Yeah, just use inverse trig. Either inverse tan of 40 over 60, or inverse sine or inverse cosine. Okay, May 31st, Wahlburgers Mall of America, show up. It's Marky Mark and Donnie time. Get a selfie with Mark. It's very important. Like, subscribe, comment below. Who is that?